If we have a single matrix, we can add it, multiply it, combine it, and that enables us to define a large family of functions or matrices rather than functions of scalar variables. Now, what happens if you have more than one matrix? We already noticed when we looked at derivative of function of a matrix that what enters is the fact that in general two matrices do not commute, and now the results will look slightly different because commutators will show up as a measure of how little the matrices commute. So let's start first with two matrices. Consider an exponential of matrix A, an exponential matrix B. And what is its relation to exponential of some of these two matrices? When we multiply ordinary exponentials, then exponents add up. That's the whole idea of computing products by using logarithmic tables. We can check very easily to at least a few leading orders what happens. On the left-hand side, what we can do is we can take exponential a plus b and expanding in Taylor series to first few terms. On the right-hand side, we take exponential of a times exponential of b, expand it to first few terms. And I'll leave it to you as an exercise, but what happens is you get an extra term, which is the difference between the two things due to b and c not commuting. And it handily gets expressed in terms of a commutator of the two matrices, meaning product of BC minus the product of CB. And then there are higher order corrections. Let's look at a situation where we don't look at A and B, but we divide them by some large number n. So they're just small corrections. In that case, when we insert this in a formula, which says that exponential of a plus b is the Euler product, and we replace each term in that Euler product by term a plus b, we can drop the extra terms. And we get a formula in which we can express a product, a matrix, the sum of two other matrices, as a limit very much like the Euler formula we know before for computing rates. This formula is very useful. We'll use it to understand how quantum mechanics works very soon. Has a name, it's called Rother product formula. Here's the next very cute thing to do. Again, I'll let you do the algebra yourself. Look at the formula of matrix B sandwich between an exponential and its inverse. Obviously, when we multiply, if B was just unity, when we multiply these two guys, we will get 1 because 3 commutes with itself, so there is no problem. And if you now do the same expansion as before, do the Taylor expansion, this guy, collect terms of the same order in this coefficient t, which we conveniently call t because in our application it'll be time, and it's just a number, a scalar number. You'll find that the first correction will be a commutator of a and b, and you can see how it happens because we'll have a times b, and then we'll have b times minus ta, so that produces a commutator. But then it becomes fun when you go to higher terms. It turns the next term, b squared, is a commuted twice with b, because we are nested commutator. The next term is T3 factorial. So this actually looks like a Taylor expansion. And it always says 1 power of b because there is only 1 power of b. But all these exponential series expanded just add themselves into iterate commutator. And, you know, it might look to you like a formula for derivative. If it doesn't, don't worry about it. But here is the relation with derivatives. If you take a derivative with respect to t time derivative, when we apply the quantum mechanics of this particular sandwich of b between these two things, sandwiched. What will happen is when you take derivative of this exponential, it will bring down factor a multiplied by the exponential. And that's how exponential works also when you have matrices. You'll get a term a times b. But when you take the derivative of this term, you'll get the minus b times a. And two of them together produce a commutator. So it turns out that when you have matrix product of different matrices, the derivative can be converted into commutator, which we'll find very useful.